again, that's people thinking that a quake is a spontaneous bad thing. And for
No,
you,
it's
they're
a
all
fantastic smooth thing.
it's fantastic smooth thing.
Yeah.
This is StarTalk, Cosmic Queries Edition. This one is titled Starquakes. Ooh. I've got as a co-host here Matt Kirshen. Matt, welcome back to StarTalk.
Thank you so much for having me. It's nice to be back.
Yeah, so you solicited questions about like stars and starquakes from.
I'm very excited about this topic, and so are the listeners. There's been a lot of your Patreon patrons have responded to this one, and we're going to try and get through as many of these as possible. But I can't promise all of them. I will try.
I don't know a damn thing about starquakes, so
Yeah, I know. I'm excited. I mean, I live in California where earthquakes are a problem, so I know how to deal with those. But I don't. If you're involved in a starquake, is getting under a table still enough, or how do we deal with it?
We're going to find out for sure. So our guest with the expertise we need is Conny Aerts. I think I pronounced that right, Conny. Welcome to StarTalk.
Well, hi. Glad to be here.
Excellent. Now you're in from Belgium and the Netherlands. You have a dual appointment. One as the professor of astrophysics at, let me get this straight, in Leuven, Belgium, and it's KU. That's Catholic University. It's like Catholic University in Leuven.
Yeah.
Is that correct?
KU Leuven. Just don't worry about it.
KU Leuven.
Yeah.
Okay.
Leuven is a small college town in Belgium. So that's where I'm from.
Excellent. And in the Netherlands, you're a professor of Asteroseismology at Radboud University in the Netherlands. And so the fact that that's even a title to hold, Asteroseismology, says how far we've come in just the specification within the broader field of astrophysics. And I think this is just delightful. And your expertise is stellar astrophysics, stellar structure and evolution. These are two favorites of mine professionally, but I never really thought about seismology in anything other than Earth. And so first tell us, what is astroseismology?
Well, it's the study of the seismology of stars. Now, as you say...
You're going to have to do better than that, okay?
Yeah, I know. Give me a chance, right? Give me a chance. So, we all know earthquakes, that the Earth has a whole crust, you know. It's not pleasant to have earthquakes, but it's fantastic to have starquakes. Now, stars are hot gaseous spheres, and they also move up and down. And we can use these starquakes to learn what's inside the star. It's the only way to know how to look inside a star. And that's just like seismologists of the Earth, you know. They are the only happy people when the Earth is quaking, let's say. Why? Because the earthquakes create waves. They travel into the planet. They bounce back at the iron core, and seismographs detect it. And then we can do all sorts of fun physics and chemistry of our planet. And we do the same, but then for stars.
Okay, Matt, I think Conny just said that while cities are burning and everyone is dying, geologists are delighted that they have earthquake.
Absolutely, yeah.
waves.
I'm hiding under a table while my pets are going crazy, and seismologists like the data. What beautiful data we're getting right now.
The data.
Yeah.
So, but I'm confused, though, because when I think of an earthquake, I have a very simple understanding of it, that you have a rigid crust that is under pressure and under tension, and then it spontaneously gives way. And then you get an abrupt shift, and that's an earthquake. But when I think of stars, they are fluids. They're gaseous fluids. So what could possibly be quaking if you don't have anything solid to build up the tension that then gets released?
Yeah, so that's a bit different, because the starquakes are happening all the time because it's a gas. And so you have motions, right? Up and down motions, but also more complex motions. And if you press a gas and then release it, it creates sound waves. That's a bit like music in a theater hall. So for me, stars are three-dimensional musical halls, concert halls, right?
Wow.
And so the nice thing is that starquakes are always there. luckily for us humans, the earthquakes die out quickly, right?
And they're rare relative. I mean, they're rare in the sense of the ones that do serious damage are rare. But as I understand it, there are actually earthquakes of even very small magnitude almost all the time. I think that's correct. Is that
Yeah,
right?
that's correct, because any body in nature vibrates. Yeah. And
Yeah.
so, yeah, stars do that all the time, and they do it permanently, which for us astrophysicists is great because we can measure the up and down motion. Yeah. Why? Because it gives changes in the temperature of the star. And so the brightness of the star changes as a function of time. And then we have our seismographs that measure these changes as a function of time.
And your seismographs are also, you implied there that they're sensitive to those boundaries where temperature changes, right?
That's
because
right.
your sound would get reflected, or your pressure wave, which we're calling sound, would get reflected or bent in a different way, and you use that to model the total interior structure of the star. Is that correct?
Yeah, that's correct. But yeah, like we cannot hear these sound waves with our ears. Huh? So we see the brightness variations because the sound is only propagating there where there is gas. And between us and the star, there's nothing. It's empty, right? So we can't literally hear the frequencies of the waves, but we see the up and down motion. And so that is actually connected. The frequency of these sound waves created by these up and down motions is connected to the physics and also the chemical composition of the star in its interior. So we can't literally dive into the stellar concert hall, but we can measure the frequencies from a distance, let's say.
But if you could,
Yeah.
you would
Yeah.
hear all of these sounds,
Yeah.
right?
That's fantastic. Sometimes I give lectures for musical artists, and then they are all totally fascinated about this, about these sounds. Like,
So let me test this on Matt. So Matt,
Yeah.
NASA's going to plan a mission to send astronauts to the sun to listen to these sounds, but it's dangerous, obviously. So they're going to go at night.
Right. you need your earplugs as well. I go to loud concerts sometimes. I don't take any chances now. I'm getting older. My hearing's going. That, by the way, I know we haven't got into the questions yet, but that actually is one of our questions from Lucas, from listener Lucas, was actually about whether you can make the heartbeat of stars into music. And,
Yes, the
and so
answer is
you're
yes.
saying yes, that you
Yes.
can absolutely
Oh
do
my
that.
goodness! So have people done?
Yeah.
So you have
Sure.
a portfolio of frequencies going on at different times in different locations, and so you got a clever musician to sort of take all of that base material and
Yeah.
figure out a way to listen to it. That'd be interesting.
Yeah. So we actually just shift I mean, each star has its own symphony, right? Depending on how big it is, how much mass it has, how old it is, it has its own symphony. But then we shift that global symphony into the audible range of humans. That's called sonification. It's a whole field by itself. And actually, it allows blind people to be astronomers. I find that for me, inclusion is very important. So in this way, we can reach people who can't see, but they can hear the stars. But we have to help them a little bit by shifting to the audible range.
We
Yeah.
have finally achieved the goals of the ancients by celebrating the music of the spheres.
Yeah, exactly. That's true.
Man, okay. So that question already got asked, Matt. So that was who asked that?
That was Lucas from New West who asked that question. And,
What is New West? What is that?
I don't know. It just says New West. I'm not sure exactly, but Lucas also precedes it by saying, I have a geek kind of question, which I don't think you need to precede any questions to StarTalk with that. I
This
think
is a
that's
geek safe space here, everybody. You don't have to preface it. But New West, I mean, I live in New York, and
Yep.
there's
formerly
just,
New Amsterdam.
just south of New England. I've
Yep.
never heard of New West. I don't know what that is. Maybe that's California after it breaks away from the San Andreas Fault.
Just floating off into the Pacific.
So why don't we get some more questions here? This is great. Now that we have some foundation for what...
Yeah, we've got some awesome ones. Some of them some of them you've already kind of answered, and I'm sure that'll happen as we go along. But I'll try and get as many ones in. So James Smith from Indianapolis says, "What is the largest recorded quake not found here on Earth? And also, do all planets have plates that shift like Earth?" A couple of people have asked that question as well. Whether all other
Interesting.
planets
So let's
have
start there
plates.
first. You know, we know Earth is geologically active because there's like volcanoes and plate tectonics. So Where else in the solar system might do that before we get back to the sun?
Oh, well, all planets will have quakes. I mean, any body in nature quakes. I was about to bang the table here, but I will not do that. But the table would also have, quakes. So they damp out quickly depending on whether you have a gaseous planet or a crust-like planet like Earth. So Jupiter, Saturn, all the big gaseous planets in our solar system, they also have quakes.
Wait a minute, Connie. You're saying
Planetary
every
quake.
sound anywhere is a quake to you.
Yeah,
Okay.
that's true. You do.
So a guitar is what we're doing right now is kind of causing the tiniest of tiniest quakes by
We're quaking
making
through
sound.
Earth's atmosphere.
Of course, you're creating sound waves.
Oh my
Well,
God.
listener Woody also asked, by the way, on this same topic, what different would the ice giants experience quakes? I guess you've said the answer is yes. And what possible differences would there be between Earth, water, ice, frozen, methane, and nitrogen quakes?
Yeah. So the
Right, that's a bit. Wait, just a quick thing. So we've
yeah.
got ice in Uranus, Neptune, the ice giants, and we've got sort of gases in Jupiter, Saturn. We've got Earth's crust here, and so presumably, Connie, you've got some portfolio of who makes what kind of sound under what conditions, so that you can decode what you hear. Is that correct?
That's correct. And so the frequency of the sound waves of all these heavenly bodies is really determined by the density of the object, right? And so stars are gases, and their density is very different from the density here on Earth
You're very low, yeah. Hmm.
or in Jupiter. Yeah. So by measuring the frequencies of the quakes, we know quite directly how big the object is and what its density is. And if you know these two, then you know the mass. So
but Connie, you
that's
said
the basic tools, right?
You said that on the sun, you measure the quakes because some parts of the sun get brighter relative to others because they're hotter. How do you do that
Yeah.
with just a planet sitting out there in space?
Yeah, we need to send some space mission
Oh,
there to come closer and to be able to see this. And so for stars, we also, I mean, this is a booming research field in astrophysics. Why? Because we recently had the luck of being able to measure the brightness variations with satellites. Yeah, we don't have a seismograph that we can put there, literally, like for the Earth, but we sent instruments that measure these tiny variations in the gas,
okay. So I'm an old world astrophysicist. So when you say we make these measurements by going there, that's cheating.
That's cheating. Yeah. We
You-
can't
you-
go there.
That's tabletop science at that
Yes,
level.
yes.
If you get to go there.
Yeah.
But you're saying it's the same kind of features in a gaseous planet. Some parts will be a little warmer or cooler than others on the surface, and that'll tell you that'll give you seismic information about what's going on inside.
Yeah. As soon as the density changes, for whatever reason, density changes give pressure waves, and these are sound waves, right?
Okay.
And
right.
and so the follow-up part from James, what's the largest recorded quake not found on Earth?
Oh, well, we have the slowest quake in a star. Like it can take several months in period. Well, for the sun, it's 5 minutes. By the way, for those who don't know, yeah, the solar quakes go up and down, create sound wave with periods of about a few minutes, 5 minutes at their strongest. So for a very big blue supergiant star, it takes months before the quake went up and down.
So just to be clear, the normal frequencies we listen to are hundreds and thousands of cycles per second. And that's what our eardrum and brain will record. And you're saying these are cycles every 5 minutes.
Yes, and that's
Or even every
fast.
Or even every month. So that's why you
yes.
have to shift it
Shift
back
them.
to our
Exactly.
audio range.
Yeah.
Otherwise, we would never even know it was happening.
That's right. These are slow waves to human standards.
Right. You'd vaporize first, but
Yeah,
Right.
while you were vaporizing, you would not know you were in the middle of a starquake. I see.
that's
So
right.
that's wild for me. So incredibly slow, but presumably hugely energetic.
Yes, that's true. Yeah. So the energy of each wave can be quite tremendous, but that also depends on the type of waves that you're dealing with. Yeah.
Okay. Wow. All right. Well, let's take a quick break, and we're to come back to more starquakes. Something was like, what? But to Connie, everything's a quake. So
Yes.
we'll get more into that in this episode of StarTalk Cosmic Queries when we return. We're back, StarTalk Cosmic Queries. We're talking about starquakes. And my co-host, Matt Kirshen. Matt, where can I find you on the internet?
Well, you can find my podcast, Probably Science. I start with the Neil episode. That's always a nice place to start. And,
I was a guest once on your Probably Science. I just thought by now it would have been called Certainly Science. I thought it was evolutionary, but
you know what?
apparently not.
The longer we do the show, the more probably it gets. It's going to descend through possibly to science.
To probably not. Okay.
And then I'm on Twitter at Matt Kirshen and technically on Instagram, but I'm very rarely there.
Okay, Kirshen, Kirshen. And we have as our in-house expert right now on starquakes, an professor of astroseismology in the Netherlands. But right now, Conny Aerts, I think I pronounced that right, is visiting New York City at a place called the Flatiron Institute, which is in the Flatiron section of Manhattan. And very cool science is happening there. All manner of science. It started with sort of math and astrophysics, but it's spilling into biology and computer science, where very deep problems that need high performance computing and clever people to solve them are invited to then gather their talents and try to solve the secrets of the universe. And Conny Aerts is on sabbatical this year. So Conny, we're delighted to have you as part of this podcast.
Very grateful to be here. Thank you.
Yeah. So we've got some more questions. But before we do that, I just want to be clear that most people's understanding of the word quake is, I think, built in is that it's abrupt and short-lived. That's kind of built into our life experience with a quake. But we now hearing about quakes on completely different timescales. Should you have invented another word to describe a quake that moves on the scale of days or months rather than seconds or minutes?
Sure, and I use the term starquakes for popular lectures, but actually in our professional life, we speak of stellar oscillations. So they're global oscillations, they're smooth, they're properly behaved. So for stars, it's a bit less abrupt than for earthquakes, let's say.
Okay. So if on Earth they were Earth oscillations, then Matt, maybe you wouldn't have to hide under a desk or in the structural beams of the house.
I would just write it out.
I'd just ride it out, surf it out. You surf it out.
Keep the knees perplexed, keep your core stable. That's all you need.
But you would get seasick all the time, because they would always be there,
Yeah, eyes on the horizon. That's the secret. Always look out the window. Don't try and look at a fixed object inside.
You take me surfing one day out in Los Angeles and teach me. So Matt, what else do we have for Connie?
We've got some great questions. By the way, just side note, I love when we have topics like this, when it's something that is close to Neil's wheelhouse, but just outside it. When it's like in your field of astrophysics, but something that you've never really encountered. They're my favorite episodes, because
you like looking how much of an idiot I am. That's what you're
saying.
Well,
I love it when we're just at the edge of Neil's knowledge. It's my favorite. It's the best.
Well, those are my favorite episodes where I learn stuff. So
absolutely.
This is good.
So I'm going to combine these two questions. I like to do this because I
want to hear their names anyway. Yes,
absolutely. Dylan and from NAU in Flagstaff and Alejandro Reynoso from Monterey have both asked about what we can actually learn from the oscillation of stars. Dylan says, can we predict its age and or understand the core? And also, do all stars oscillate or just dying stars, supermassive stars, main sequence stars? And then Alejandro says, what have you learned from analysing starquakes that you couldn't learn with other methods? So basically, they're both asking, what specifically is it that we can learn from these quakes? And
I'm going to tighten that question and say, what are you learning that we didn't otherwise figure out through other means?
Okay, if there's one word that I have to ask to that question, it is rotation of stars. That's more than one word, but internal rotation of stars. And why is that? Let me give the analogy with music again. So we have sound waves that are happening inside a star, but the gas in the star is rotating around, right? And what do you get when you put a musician in a theater play and you make the podium rotate just for the fun of it as a surprise to the musician?
You get pissed off musicians.
Yeah.
That's what you get.
Exactly. I like that experiment, actually. You can really do that. But the symphony is destroyed. That's what the audience would say. Now, for me, as an astroseismologist, the frequencies of the waves get shifted, right?
The Doppler shift.
Yeah, they get shifted because of the extra motion due to the rotation. And we can measure that. And we're not measuring that at the surface of the star, but inside the star where the starquake has its strongest energy, right? And so what we have come to realize is that the theory of how stars evolve, relying on how they rotate in their interior, is quite off. It's not very good. And that's not surprising, right? Because we could only measure, before we had starquakes, we could only measure the rotation of the star at its external layer. Like for the sun, you see the tiny little dark spots of the sun rotating around. If you're patient, every 26 days, you see them back in your line of sight. But so the sun rotates with a period of about 26 days, but that's just the outer layers. It doesn't say at all how it rotates in its interior. So if you have no information, what can you do? Well, you think, well, it won't be that different.
You just assume
right?
it's the same, right? I mean,
You assume it's the same.
everything else rotates as a kind of a unified object. Why
Yeah.
would I even think some lower level would rotate at a different rate?
Well, the stars have many more surprises than us astrophysicists have imagination. Huh? So what
What a smack! Oh, Matt, did you hear Matt? Matt,
Yes.
did I just hear this woman correctly here? Did you-
Yeah, I stand by it. I'm on Team Star on this one.
And,
that was a smackdown right there. Okay.
yes, I always say the stars are right, the theory is wrong if it doesn't match with each other, right?
Uh-huh.
So thanks to the frequency shifts of these waves, we can now measure how stars rotate around. And why is that important? Well, if they rotate faster or slower, then their material gets mixed in a different way. Yeah, that's also something you can imagine if you take the analogy with coffee drinkers. If you like coffee with milk, you pour milk into your coffee and you don't wait until everything is mixed, because then the coffee is cold and it doesn't taste well anymore. No, you take a spoon and you rotate your coffee. In my terminology, that is saying you bring angular momentum to the coffee cup. And why do you do
That's
that?
what everyone says when they're having coffee at Starbucks.
That's
They
what
all say that.
everybody does without saying it. And that's because everybody prefers well-mixed coffee with
Yep.
milk. And
I'm assuming at the
yeah.
Flatiron Institute that just the coffee station there has angular momentum implements.
Yes.
Just-
How much
Yeah.
angular momentum would you like on your coffee this morning?
Just
Yeah.
do you want a metal angular momentum implement or one of the wooden straight ones? It's
Well, we could do an experiment of how people do that. Huh? But, the diversity of human beings taking their spoons will be large. And in stars, there's a whole range of internal rotation frequencies that we have measured. We have about 2,000 stars now for which this has been measured by many groups in the world with astroseismologists. And so the life of the stars is really going slower if I look at the measurements.
You mean our estimates for their life expectancy need to be updated to have them live longer than we originally thought? Is that what you're saying?
Yeah, particularly for the big massive stars.
Is that because they're mixing more material into their core?
Yeah, they're
Giving them a little
mixing,
more
yeah.
lease on life?
Yeah, and they get more material into their inner part. And in the inner part of the stars is actually a nuclear reactor for me, huh? Because the simplest constituent, which is hydrogen, is turned into helium by nuclear fusion. And stars are masterpieces in that. But if you bring more hydrogen into that area where it's hot and dense enough, then the star can live longer. And so the rotation affects how much nuclear fuel you bring inside its interior, actually.
That was about to be the opposite of what I would have guessed, because I was wondering whether the sort of the stirring effect would have sped up the fusion reaction by kind of, you can increase the speed of a chemical reaction. I know that's different from a nuclear reaction by stirring the chemicals together or by increasing the energy in there. But you're saying it's the opposite because it's bringing more fuel in from the outside layers of the star.
Yeah,
Right,
so once
right.
the nuclear burning is ongoing, the nuclear fusion in stars is stable. Stars can do that very well. We humans can't do that here.
Now, everything I know
yeah.
about the nuclear furnace says that it's pretty small relative to the size of the star itself. Do your waves give you enough information about tiny areas like the nuclear core?
Yeah, well, tiny. It's 10% of the mass that they typically takes part in the nuclear fusion. So it's still 10%. It's not
Of the
that
mass,
small.
even if it's physically
mass.
small, it's got a lot of mass going on.
Yeah,
Okay.
because the density is very high. And so
Right.
if you change that 10% to say 12%, that sounds like, it's only 2%, but that's a lot of fuel, huh?
Yes.
That you bring into your nuclear reactor. And
Right,
so then
right. And increase the life by at least 20%, perhaps, or you think maybe.
Yeah, it can really change the lifetime of the star. So that's so. To come
And
back-
Matt, if you were in the center of a star, you'd be dense too. I just wanted to tell you that. Okay.
Oh, thanks. It's one of the nicest things anyone's ever said to me. But
We got more questions, Matt. Bring them on.
we do.
Keep them
Aziz
coming.
from Saudi Arabia says, I wonder if it's possible for a star to have a starquake so strong caused by, for example, nuclear fission or fusion happening or abnormally fast, or caused by any other reason to lose mass. I thought I'd ask that one because we're already talking about fusion.
In the formation of stars in the galaxy, you can get shock waves across a gas cloud that's otherwise minding its own business, and it can trigger gravitational collapse and other interesting features. So I'd love that question, Connie. So are starquakes just the product of what's going on, or are they a participant in causing what's going on? Ooh.
Yeah, so you can have all sorts of reasons why stars have these oscillations, right? And they can indeed be caused by the fierce turbulence in the core of a very massive star, because it's we call that convection, turbulent motions, and they create waves also because again they make the gas compress and expand. But there are also other reasons why stars can have starquakes. Think of the Earth-Moon system and tides. Well, half of the stars, or even more if you go to higher masses, they live together with two. And then they have
A
tidal
binary
forces.
star system.
Binary
Just like
star
in that
system, yeah.
scene in Star Wars where Luke comes out, is it the sand planet, and he sees a double sunset. That's the only accurate science in the entire series.
But that's okay. That's okay. Yeah.
Okay, so what happens there? So you have a gravitational tidal dance.
And that's right. They rotate around each other and they pull. They give a tidal pull, right? And so you could also say that, for me, tidal forces are actually forced oscillation. I say everybody oscillates in nature. So when the stars are close enough together, the tidal oscillations, as I call them, are very strong, can be very strong. So that's another reason why stars can have.
So these are like a
starquakes.
tidal
Yeah.
bulge in the direction
exactly.
of the
Yeah.
object responsible for
Yeah.
it.
Yeah.
See, in my older years, I have a tidal bulge as well in my midsection. I'm watching for that just to see
Yeah.
what I can do about it.
Yeah. Yeah. You want to prevent it, but
You
we
want
like
to
it when we start it. Yeah.
All right, Matt, give me some more.
Quentin from Switzerland says, and I don't know what Quentin's referring to, so hopefully one of you two can fill me in. Says, do you need more data to exactly figure out what happened with Betelgeuse recently? Is it pronounced Betelgeuse? Betelgeuse?
Betelgeuse,
It seems,
yes.
It is pronounced Betelgeuse, like the film, but spelled differently. It seems pretty unlikely that we will witness a similar event in the near future. So what is it? What did happen?
I got to
recently?
lead off with this, and then we'll get the actual answer from Connie.
Okay.
I heard, but Betelgeuse is one of the brightest stars in the night sky. It's a important star in one of the most dominant constellations of all 88, dominant in size and appearance, is Orion. Orion is visible in both the northern and southern hemispheres because it straddles the equator on the sky. And so there's this star, Betelgeuse, one of the biggest, baddest red giants in the known universe. And someone told me, do you realize Betelgeuse is getting dimmer? I said, no. What? And I looked up and I went, it was because my whole life, Betelgeuse was a certain brightness relative to other stars in the constellation. I cannot communicate to you my loss of breath in the moment I looked up. And I say, what is happening? Is this, is this, is the seventh seal broken? Is this something biblical? So, Connie, I want you to know.
What's going on?
Yeah.
I nearly freaked out. So what happened to Betelgeuse a year ago when it just got mysteriously dim? Like it went to less than half its normal brightness, and that had never been observed ever in any time anybody's been looking at the star. So we're going to blame you for this, Connie. What happened?
Well, Betelgeuse is behaving normally as a star. It's it's a supergiant, right? It's a very big star. And so these stars are nearing the end of their life, and so they're puffing up their material and they're blowing it away, so to speak, right? And so when material gets lost from the star, well, then for us, the star is obscured because it's in between the supergiant and us. There's material that is being expelled. Right? Now, for me, as an astroseismologist, that's a bit annoying, that behavior, because Betelgeuse has starquakes, but all that material that's being expelled makes it hard to still measure them.
It's blocking your view.
It's blocking the view. And that's also the reason why, for us, it's difficult to do astroseismology from ground-based telescopes. The stars are up there. People say they twinkle, right? But that twinkling that you see with your eyes, that's not a star. That's actually the starlight that is being perturbed by the Earth atmosphere, right? And so it's a bit similar, but then the twinkling of Betelgeuse is caused by the material it has expelled. But it does have also oscillations, and these oscillations can tell us how old it is and how big it is, etc.
All right, it's Betelgeuse ready to blow because we think that's a supernova category star. Is it?
Yeah.
I said, oh my gosh, something bad's going to happen.
It's going to happen. It's not bad. No, it's not bad. Because it will explode eventually, but that can take still some while. So, you don't want to go and look every day because you may need to have some patience. Like
Connie, we're trained to think that if something blows up, it's bad. Okay, I'm sorry.
No, but these guys are like, it's exciting. This is more data.
It's more data. Okay,
yes.
All right. This is like the rocket launchers who. The rocket blows up on the launch pad. You say, oh, are you upset by that failure? No, that was an experiment rich in data.
Yeah.
Okay?
Well, but I'm saying it's good because it enriches the galaxy with metals, with carbon, with oxygen, with iron. And, we need that as human beings. So,
okay, just to be clear, Matt, astrophysicists we are very lazy with regard to the periodic table of elements. And so any element that's not hydrogen or helium, we call it a metal. But this freaks out chemists, okay? We're self-aware of this bad vernacular, but the point is 98% of the universe is hydrogen and helium. And the rest is just other stuff. So we just
experimental error. It's just
so we just call them metals, and I'm just covering Connie's ass right here when she said the metals such as carbon. Right? No, she's being fully astrophysical in the referencing. So, but Connie, you speak of this blockage of ejected gas. Like, of course it would do that. Yet it hasn't done it in the thousands of years we've been observing the night sky and mapping its brightness relative to other stars. So do you have an account for why it's doing it now and it's not doing it regularly?
Oh, but you see, we astrophysicists have to be very patient because the timescales, for stars to do this kind of stuff, that's like hundreds of thousands of years, and And
Okay, so you're saying if we'd see it only
yeah.
once in a few thousand years,
Yeah,
that
that's
could be
normal.
a regular interval.
Yeah, yeah, yeah.
Okay. All right. She got out of that one, Matt, I think.
It's just
She's a
annoying
pro.
that we human beings only live for like 100 years, like
At most,
if
yeah.
if we are lucky.
Yeah, we're
And so
very
that's
lucky.
in an astronomical time scale, that's instantaneous. That's very
Instantaneous.
short. Yeah.
All right, we got to take our last break. And when we come back, more astroseismology with a professor of astroseismology, Conny Aerts, on StarTalk, Cosmic Queries. We're back for the third and final segment of StarTalk, Cosmic Queries, the Astroseismology edition. With our expert, a professor of astroseismology, Conny Aerts, and she's on sabbatical now at the Flatiron Institute in New York City, which has gathered all manner of computational scientists in multiple fields, where they not only compare notes with each other in their own field, but across disciplines. Perhaps there's some cross-pollination that can lead to discoveries that wouldn't otherwise happen. And Connie, you are based in the Netherlands and in Belgium. You have two different
Correct.
appointments.
Yes.
That, of course, there's strong overlap in what they are, but this is very cool that we have you here. We're borrowing you from Europe, and great to have you here in my hometown, New York City. So, Matt, we have a few minutes for a few more questions. Let's see how many more we can slip in.
Let's try and go quicker
these
on
questions
this
are
one.
from our Patreon members still, correct?
They are, yeah. So Kevin the Sommelier asks, does astroseismology coincide with the data we can get from the James Webb Space Telescope? Are we able to see those quakes in infrared? And then
Ooh, I
also
like that.
asks, yeah, and also then gives a wine recommendation.
Oh, yeah,
from
because I told him I
for our
would not,
Belgian
I
guest.
would not allow him to ask another question. If he's going to bill himself as a sommelier, there's got to be a recommendation in his
So he
question.
recommends specifically for our Belgian guest, says with Moule Frites, Kevin recommends a bottle of Muscadet sur Lee Lagrange. So there we go. Thank you, Kevin, for that.
Okay, that sounds like a dessert wine. All right. Let the world know. Okay, we got the recommendation.
Yeah,
So I love
James
that
Webb.
question, Connie. I didn't even think about this because I love stellar evolution, but I'm primarily a galaxies guy and a large scale structure guy, which the James Webb Telescope is exquisitely tuned to observe the early universe, and it would never occur to me to imagine if it could be of use to you in thinking about starquakes. So how is your field put your sort of hooks into the data of that telescope?
Well, the James Webb is fantastic, huh? But I would not spend its time on starquakes. And so let me explain why. James Webb can pierce very deep into the early universe in the infrared. But what I need as a seismologist is really long-term measurements. And that's why we love the Kepler mission of NASA and now the TESS mission and the future PLATO mission, because they're staring at stars for years without interruption. And so you don't want to spend James Webb on that because it has, as you say, so much other fantastic extragalactic science to do. So I
Interesting.
don't want to hook on James Webb, right?
Of course, at all times in our field, Matt, we're always judging whether you need one particular telescope for that task versus another telescope that might be either more available or less a cutting edge, because you want the cutting edge telescope for the cutting edge science that's going to break open whole new fields typically. So yeah, that's a very important point that you're mentioning there, Connie. But I want to also ask, that's part of the great computational challenge, because if you have a lot of quakes of all different frequencies, short measurements cannot distinguish one from the other, correct? You need a very long baseline so that you can tease out of the data frequencies that are represented enough to know that they're real. Did I characterize that?
Yeah, that's very well described. And in practice, the precision of the frequency goes as 1 over the total time base of the measurements. Yeah. So if Kepler measures 4 years, well, that's 1 over 4 years in frequency resolution, as we call it, capacity to unravel these starquake frequencies. So we need to be very. Astroseismologists are very patient people.
So what you're saying is if you, so I like that. So if you measure something for 4 years, you can't really say much about frequencies that occur on 2-year timescales because you'd have only had 1 or 2 cycles in there, and that's not enough to even know if they're real.
Yes.
So you need enough cycles in your baseline of data to be able to say, yeah, that's real. Yes, it's repeating, and it's reliable.
Yeah, that's right. And so that's why we need these long time series, and we can only do the work once we achieve that. So we need dedicated space missions to achieve that. And James Webb is just not one of them.
I got it.
Again,
Interesting.
Please leave James Webb to the people who need it. And
Okay.
I'm not one of them, all right?
That's very magnanimous of you, yes.
Yeah.
So just to update people, so Kepler was a telescope that looked in one part of the sky, looking for Earth-like planets around sun-like stars, studying them for a long period of time. TESS, what's that? That's an acronym for what? I forgot. Transiting
Exoplanet
Survey Satellite. Thank you.
Yeah.
So TESS will see the entire sky, but not quite to the depth in space that Kepler did. And so now what is PLATO going to do? And is that also an acronym?
Yeah, well, PLATO stands for Planetary Transits and Oscillations of Stars. And PLATO is actually gonna, from construction, combines the best of both worlds of the Kepler mission and the TESS mission, in the sense that we need long-term observations, but we also need the whole, not the whole sky, but a very, very big part of it, to have copies of the Earth in our line of sight that rotate around copies of the Sun. It takes a year for us to revolve. And so PLATO has that built in. It's actually, it's 24 telescopes on one big platform.
Oh my gosh. Okay, I didn't know that about it.
Yeah,
Okay.
so it's a multi-telescope instrument that is being built by the European Space Agency right now. I tend to call it my third child because I've been in.
Oh, you're deep involved in the design and
yeah.
objectives of it. Well, congratulations for that.
Yeah. So that's exciting. I want to see the data before I retire. Yeah.
Kepler was a famous German mathematician who coincided with Galileo, actually, in time, and we all heard of PLATO, but I don't know any TESS. So TESS was an acronym, but not an acronym of a famous scientist of the past.
Exactly.
Okay.
Yeah.
So they don't always work out the way you need to.
Yeah. Just as long as the machinery works for us, astrophysicists.
You don't care what the hell you call it. All right, so Matt, keep it going. What do you have?
I am gonna try and get through as many of these questions as possible. I am gonna try and combine
test
four
Connie,
different.
See if she can do a lightning round.
Here we go. We're combining 4 questions. They said it couldn't be done, but 4 different questioners because a lot of people have asked about the effect of sunspots on starquakes and how they affect Earth. So Charles Mako asks how they affect starquakes. Trevor Mills says, how close would a nearby star have to be for a starquake to be considered dangerous for Earth? And then Sarah Rosen says, how big of a CME would it take for the sun's gravity to be negatively affected? And Gina Martin says, why didn't the starquake back in 2004 wipe us out? I've read that it released more energy than our own sun would emit in 150,000 years.
Okay, so let me tighten all those up. So Connie, clearly there are quakes going on all the time, and I presume that a CME, a coronal mass ejection, is itself detectable as some kind of quake activity. So, and of course, sunspots are measures of the activity of the sun. So, but you haven't mentioned solar flares or coronal mass ejections or sunspots yet, not much in this conversation. So what role do they play in all of this?
Oh, well, the role they play is they disturb the periodic oscillations of the sun, but it's not bad for us. Why not? Because a coronal mass ejection or star spots that rotate around, they do not give the same signal in the periodicity of the quakes. I'm quaking my microphone right now. A coronal mass ejection is an abrupt event. It's more like an earthquake, you could say. It happens and it disappears, right? But it doesn't disturb us finding the 5-minute oscillations of the sun, which are always there. Yeah, they get disturbed abruptly, but then they continue and they continue and they continue all the time. So for us, we can unravel the signal of star spots, of mass ejections, even for stars other than the sun, from the always smooth periodic oscillations. So
All right. So how about the dangers that they might pose if you do have a coronal mass ejection that happens
Yeah.
to head towards us?
Yeah, so the Earth is protected by a magnetic field that protects us from all these high energetic particles falling in on our planet. And other stars are too far away. So, I mean, it's only a matter of the solar quakes. They are not dangerous for us. The coronal mass ejections, they disturb our electronics every once in a while, right? But, that's not a periodic oscillation that I would call solar quakes.
Yeah,
Right?
I forgot that you enjoy events like that, even if they mess with our computers. Okay.
That's how we
That's-
started. Yeah,
I forgot
yeah.
that. I learned that
Yeah.
earlier in this podcast.
Yeah, that's
So that
true.
almost counts as a lightning rod
Yeah.
round, Matt, because she answered 3 questions in one reply. So
She did.
Let's see if we can get a few more in before we call it a day.
Yeah,
here.
James Allen from Brisbane in Australia says, could a starquake large enough theoretically cause a star to tear apart? And would this send a high radiation blast like a supernova? What could we learn such things from our own star?
A starquake would not rip apart a star because it's really a smooth, nice periodic variability. The biggest starquakes in terms of expansion and contraction, let's say, can make the star become bigger and smaller by about 10% in its radius, let's say, but not make it explode. That's another phenomenon.
Okay. Again, that's people
Yeah.
thinking that a quake is a spontaneous bad thing.
Yeah.
And for
No,
you,
it's
they're
a
all
fantastic smooth thing.
It's fantastic smooth.
Well, on that same note, Connor Home from Squim, Washington says, is it possible to predict where and when a starquake will occur? And if so, what's the largest predicted starquake, and how much bigger is it compared to the largest recorded one?
Well, starquakes happen all the time. I keep repeating that.
So let me
yeah.
ask it differently then. What variety of your oscillations carries the most energy?
Well, the simplest starquakes are radial oscillations, up and down and up and down. So everything is expanding and contracting while keeping spherical symmetry. So that's about the largest energetic it can get, and that's for me just a simple oscillation because
And
it's
that's
a
what gives
radial
us
oscillation.
variable stars, I guess, right?
Yeah. So Cepheids are Lyrae
Yeah, I mean,
stars.
it's half a star. I mean, some huge fraction of stars in the night sky are variable, presumably for this reason. And I heard when I was in graduate school, Connie, that if you looked at every star close enough with sharp enough data, they're all variable.
Of course they are. Everything oscillates. Of course.
So we just have to draw some arbitrary line of
Yeah.
what we catalog as a variable star relative
Sure.
to other stars. But really, to you, everybody's got action.
Well, we're measuring the action up to parts per million,
Yeah, there it is.
right?
You got it.
Parts per million.
You got
That's
it. Okay,
good. That-
Matt,
that-
let's get one
yeah.
more. Slip one more in before we got to call it.
All right. Margaret Defoe from Milwaukee says, why didn't our solar system go binary? And what is the smallest
Oh.
and largest a star can get? So we're on more general questions about stars. I think.
Yeah,
Yeah,
let's do. Hold aside the largest and smallest. That's a whole other astrophysics
Yeah.
question. But Connie, what do you say about why the sun is alone when so many stars in the night sky are binary in multiple systems?
Yeah, well, if you look at a star with the mass of the sun, then half of them are in binaries. So that means that half of them are alone. So
Oh,
it's a toss. It's an equal toss, right? Yeah. So that's not so exceptional. But if you go to stars,
That's not the answer we were
Yeah.
looking for. We wanted you to
Yeah.
say we
Yeah.
might have had a double and then
Yeah.
it blew up. We want a
Yeah.
more sci-fi answer here.
We lost. It was originally a twin. We lost one of them. It ate the other one in the womb.
It
It's,
ate the other
Yeah.
one.
I don't think so. I don't think so. But that happens frequently when you go to higher masses. Huh? If your star is born with 10 to 100 times more mass than the sun was born with, well, then about 80% of the stars are multiples, double stars. Yeah. So for the sun, I think it's just a logical consequence of there only being half of them that live their life together.
Okay.
Right?
All right.
Luckily for us, it wouldn't have been so nice here if it would have been living next to a star that has exploded already. Not
Yeah,
nice.
yeah.
Huh?
It has issues, but that's definitely a yet to be written sci-fi drama.
Yeah.
I think a
Yeah.
sci-fi action film.
Yeah.
Whatever happened to the sun's twin? You got
Yeah.
it. Well, Connie, it's been a delight to have you on StarTalk. And like I said, my city, my town is your town. So I'm a native of New York City. You're visiting for the sabbatical. Maybe we can get you up to the museum and give you a tour and possibly extort a seminar from you for our astrophysics group.
Yeah. I love this city, so I'm very grateful that you were hosting me.
Excellent, excellent. Matt, always good to have you, man.
Oh, it's a pleasure to be here. Thanks for having me. And this has
Okay.
been great. I've loved hearing about this stuff.
So thanks for joining us on this episode of StarTalk Cosmic Queries, Starquakes. I'm Neil deGrasse Tyson, as always, bidding you to keep looking up.